purpose of this clip is to identify situations in which mechanical energy is or is not conserved. And that will allow us to further use the law of conservation of energy to solve additional problems. This example problem deals with a wedge that we have a block resting on top of it. Now that block is free to slide down this frictionless incline, but once it does, it's going to reach a flat surface that does have friction, and it's going to slide up until it comes to a stop. And we want to know how far will it slide. So first of all, right off the bat, just because this thing slides and it comes to a stop, just based on the question alone, you know that mechanical energy is not conserved. You know this because it used to be moving, and it used to be up at a higher elevation, and it ends up at rest at a lower elevation. So we must have lost energy somewhere. Where did we lose it? Well, we lost it to friction. And we're going to find out exactly by how much we would have lost, how far we could slide. So let's go to the law. Energy initial, total, has to equal total energy final. Now in the beginning, because we did have some height, that means we must have had some gravitational potential energy. Now we do have kinetic energy from the beginning, between the beginning and the end points, but at the very, very initial beginning, we don't have any kinetic energy yet, so it doesn't belong there. But we will be losing some energy to non-conservative work. And in the end, we have zero. We have nothing. We don't have kinetic energy. We don't have potential energy. It's all gone. We came to a stop at the ground. So what that means is whatever gravitational potential energy initial we had, that all gets converted into the non-conservative work, which converts it into, say, heat in this case. So gravitational potential energy initial, that's quantified by mgh, and work we know is quantified by force times distance times the cosine of the angle between the force and the displacement. So that negative sign is going to end up canceling, because this angle right here is 180 degrees. That's the angle between the force of friction and the direction that we actually move. Let's draw the rest of the free body diagram. So the force of friction is actually quantified by mu times n, as we remember. And in this case, n is just mg. So I can say this is all minus mu mg. Now that's multiplied by the distance that's unknown. I'll leave it as d. We're trying to figure that out. Times the cosine of 180, well, that's -1. So again, your negative signs get deleted there. So then we've got mgh equal to mu mgd. And you've got m on both sides, so it's not going to matter. Isn't that pleasant? And you also have g on both sides in every term, so that's going to cancel as well. And so then our algebra becomes easy. The displacement then must be equivalent to the height divided by the coefficient of kinetic friction. So that is just 1 meter divided by 0.3. So then the distance traveled is 3.3 meters. Okay, you try one. We've at an example where a Newton cradle with only two balls A and B loses 10% of its mechanical energy with every collision. So if you initially start at this angle of 60 degrees, which would give you some height, h initial, hi. We're asked, or you're asked, how much height should you have on the return swing. So it's going to knock ball B up a certain amount. It's going to be up here later on. And then that's also going to swing back, hit ball A again. Ball A will subsequently continue up, but how much? How much will it go up the second time? That's your question.